Welcome to Synthetic-Metals.com's third video on performance tuning nanothermite using performance tuned ferric oxide. In this video, we'll be examining the correlation between thermite powder volume and thermite energetic performance. Reminder from Chapter 1, there are four types of ferric oxide powders. Far and away, the vast majority, call it 98%, of all thermite made is made using solid micron-sized particles. This is the industry standard. Researchers will use solid nanoscale particles, and the remaining, call it 0.1%, is custom made using proprietary nanoporous powders like what you will see in this video. University of Minnesota published their proprietary nanoporous powder research in 2004. Note that their particle size was in the 100 to 250 nanometer range, which is large for a nanoparticle. We began work on our nanoporous micron-sized particle around 2008. So far in this video series, 3 different nanoporous ferric oxide powder qualities have been tested. Far and away, our best powder was that you saw in Chapter 1. It was dialed in, meaning it passed our PO4 test. Powder tested in Chapter 2 was an array of PO4 test failures. Both Chapter 1 and Chapter 2 particles were synthesized at our first site. Powder tested in this chapter was our first attempt to replicate Chapter 1 powder quality at a new site using upgraded equipment. Our first attempt came in well off the mark. Our first production run at the new site using upgraded synthesis equipment produced 6 samples labeled in this picture as pots number 2 through 7. The reason pot number 5 is empty was because the sample size collected was insufficient for thermite firing. No videos were taken of this first production run due to systemic ignition failures. Look closely at the picture, and while all 6 pots contain the same weight of powder, 12 grams, you will see that the volume of powder in each successive pot, generally speaking, is slightly larger than the volume of powder in the prior pot. Missing from round 1 pictures was a pot containing solid nanoscale ferric oxide powder, so we added it to our round 2 testing. Again, note the volumetric differences between the solid micron and nanoscale particles versus our solid proprietary nanoporous powders. Again, the powder weight in all 5 pots is the same, 12 grams, 9 grams ferric oxide, 3 grams aluminum. First up, solid micron-sized ferric oxide. Next up, solid nanoscale ferric oxide. Third up, nanoporous micron-sized ferric oxide. For sample 3, the sample size collected was sufficient to allow for 2 firings. Fourth up, nanoporous micron-sized samples 5 and 6. Last up, nanoporous, micron size, sample number 7. In summary, burn durations were as expected. Sample 1, using industrial-grade micron Fe2O3, had a 25-second burn duration. Sample 2, using research-grade nanoscale Fe2O3, had a 34-second burn duration. For sample 3, the average burn duration was 43 seconds, as was sample 4's duration. Sample 5's duration was 42 seconds. Compare the 43-second burn duration of Chapter 3's nanoporous powders with the 1 to 3+ minute burn durations of the 4 best nanoporous powders tested in Chapter 1, and the impact that nanoporous particle architecture and surface area has on thermetic energetics becomes quite clear. Now, in a perfect world, we would have taken powder volume pictures of all 7 pots of Chapter 1s before firing to further correlate this theory, but because that did not happen, we'll need to look at future videos for that evidence. In conclusion, in this video, increased powder volume correlated to increases in both thermetic flame intensity and duration. In future videos, dialing in quality control at our new site will produce incrementally improved powders for testing, which you'll see in subsequent videos.